Okay, welcome back to this class. So now we're going to be looking at errors and types of errors. We're going to be seeing this as part 2. Now, I want us to know that errors are grouped under two major headings, which are systematic errors and random error. Note that these are the two major types of error we have: systematic error and random error. There are other types of error we have, but they are classified on either they are systematic or they look like random. So first of all, let's see what systematic error is. I'm going to read out. Systematic error is that error which affects readings in regular way. It affects readings in regular way. It causes the reading to be consistently high or consistently low. Let me I will make an example of that and I will explain that. It causes the readings to be consistently high or consistently low. Another thing is that this error is mostly due to faulty instruments. Systematic error is due to faulty instruments. Now, how do you minimize systematic error? Systematic error can be minimized by using several independent systems of measurement. I repeat, it can be minimized by using several independent systems of measurement. So, having known much about systematic error, I want to explain a little bit about systematic error. Now we say it is an error that affects the reading in regular way. How is it in regular way? It causes the reading to be consistently high or consistently low. And this reading is as a result of error in measuring instrument. Like example now, if I'm working with a stopwatch, you know that when the stopwatch is not reading anything, the arrow is supposed to be like this, pointing at 0. Now, but you see some stopwatch, they are not reading anything, but let me just say this is. Now, you see that this stopwatch is not pointing at 0, it's pointing at 0.2. Now, it's an error already. The stopwatch already has an error. So if I use this stopwatch to measure my instrument, it will be giving me a reading that is 0.2 ahead. That's why we say systematic error. It gives a reading consistently high, or if this thing is like this, you see it's already reached 0.3 behind or consistently low. So if I've got my answer here to be like 5.2, it should be normal, supposed to be 5.0. But because I'm using an error-prone measuring instrument, so it will be giving me my reading to be consistently high. So that's what we mean by it makes the reading to be consistently high or consistently low. It's just like when you go to fill up your gas in the gas station or people that fills up gas. Now, if you watch their scale, and this is where your cylinder is sitting. Now, if you watch, there's supposed to be 0 here, and you see the scale already reading. When you have not even put your stuff on it, it's already reading 0.1. So it is very wrong. It will make, instead of it to feel 5 kg, you may be feeling 4.8 kg, or you may be feeling, and you know, they don't want with them, they are very smart. They will not let it be reading above. They always want it to be reading behind, so they will be gaining instead of you gaining. So be very careful. So that is what we just call systematic error. Now, how do you minimize? Now, remember that errors cannot be eradicated. It can only be minimized. Okay. So how do you minimize standard error? We say we use several independent system of measurement. That means use different, like you want to measure time. Stopwatch can measure time. You have stopwatch on your wristwatch also. You have other instruments that can measure time. Use different, like 3 instruments, and you will see the one that is having error. If this one read 5 minutes, this one read 5 minutes, and this one is reading 4.2, you know that this one is having error. So using several independent system of what? Measurement. Okay, that is for systematic error. Let us come to random error. We say this is an error. These errors are irregular and fluctuating in magnitude. Random error, they are irregular and they are fluctuating in magnitude. That means their value you are going to get is fluctuating. You know what we mean by something is fluctuating? Okay, this is as a result of limitation of the observer to read exact value from the graduation of the instrument. Now, for random error, it is the error due to the observer. Now, what of when the instrument is very okay and the error and the observer, person taking the experiment, cannot actually read? There are some instruments you cannot make use of because you don't have idea or the skill to do that. Now, if you are given such instrument to use, like the vernier caliper, most of you will find it difficult to read the vernier caliper when you were doing your experiment. Now, you see, you start reading wrong readings from the vernier caliper. Your reading becomes fluctuating. Sometimes it can go low, it can go high, it can be off the mark, fluctuating, not being, the stable. So in that type of situation, the vernier caliper you are talking about now is okay. There's nothing wrong with it. But the observer, which is you now, could not take good reading from it. So you say that the fault is from you, and that kind of fault is what we call random error. Another type of random error is when you cannot record the exact value you are seeing there. Instead of you to record 0.5, you are recording 0.7. That is a random error. Now, how do you minimize random error? You minimize random error by taking multiple reading, and at the end of the day, you take what now? The average. That is to say, for me to run away from random error, I will take reading more than 2 times. Like example, T1, when you are doing your practical simple pendulum, you took your T1, T2, T3. Then you now do T1 plus T2 plus T3, all divided by 3. You now get a value of T. What are you actually doing there? Why not just take only 1 T? You are trying to avoid random error. So random error is being avoided or minimized by taking several readings and at the end of the day taking their mean. You take several readings and at the end of the day you take their mean. So that is how you reduce or you minimize random error. So we say random error is an error due to the observer, while systematic error is error due to the what? Instrument. Now I want us to note something, that a measurement is said to be of high accuracy if the systematic error is small. So if you can ensure that you minimize this your systematic error very well, and your random error, the observer is okay, and the systematic error is very small, the readings you are going to get are said to be what? Accurate. And it is said to be precise if the random error is small. When the systematic error is small, the readings are said to be accurate. But when the random error is small, the readings are said to be precise. So mark that. Accuracy and what? Precision. Lower systematic error talks about accuracy. Lower random error talk about what? Precision. Okay. So we are going to see other types of error, though they fall under this class. Okay. We're going to see other types of error, though they fall under this class. The first one we're going to see is standard error. We're going to see standard error. This is a type of error that assesses the precision of arithmetic mean. It assesses the precision of arithmetic mean in a large number of measurements. It assesses the precision of arithmetic mean in a large number of measurements. Now, standard error in mean is given as range over number of observations. Standard error in mean is given as range over number of observation. Okay? The next one we want to check is what we call fractional error. For fractional error is also known as relative error. Fractional error is also known as relative error. It is calculated as, fractional error is calculated as error over actual value times 100 over 1. Fractional error is calculated as error. In fact, let me put it this way. Fractional error is calculated as error over actual value, while percentage error is calculated as fractional error times 100 over 1. When you multiply fractional error times 100 over 1, you have percentage error. While fractional error is error over actual value. Standard error in the mean is range over number of observation. Okay? Let us see an example that will clear us on this, and this. Okay, let's look at one example to drive that point home. It says, in a rolling cylinder down an inclined plane, the following results were obtained. Look at the results. The question answer, we should calculate for the mean, standard error in the mean, fractional error, and percentage error. Now, for the mean, sum of the reading over number of reading. That means you add all. This plus this plus this plus this plus this. Sum all together. Then over the total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. My own is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, my own is 10, so I have to do for my 10. So let me sum all together to see. I have 6.20 plus 6 plus 6.3 plus 6.2 plus 6 plus 6.4 plus 6 plus 6.5 plus 6.4 plus 6.7. That gave me 62.7. Okay, 62.7 here. My own is 62.7. Like if I add all, then 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10 over 10 divided by 10 will give me 6.27. Okay, 6.27. That give me 6.27. Okay. Now, okay, haven't seen that I've added all. Haven't seen that I've added all. I got this divided by the total. I have 10. Give me this. Okay, the next one is standard error in the mean. This is our mean. Our mean is now 6.27. We want to find the standard error in the mean. It's going to be the range over number of reading. My range is the highest minus the lowest. If you look at all this, the highest number here is 6.7. Why the lowest to be 6.0? So it's going to be 6.7 minus 6.0 over 10. Over 10 now, because I'm using number of 10 over 10. So I'm going to be having 6.7 minus 6 divided by 10. And that gave me 0.07. 0.07. So this is my standard error in the mean. Please, when you are putting about standard error in the mean, you plus or minus 0.07. So that means my mean will now be reported as my mean plus or minus the error. My mean plus or minus the error. That's how we report it. This is your mean. This is the error in the mean. So you report the mean with the error together. Number 3, say fractional error. Fractional error is error over actual value. So see the error 0.06. Then the actual, okay, 0.0. This is now 0.07 here. So here will be 0.07 over the actual value. My actual value is 6.27. So 0.07 divided by 6.27 will give me 0.011. So I have 0.011. So let me leave that as that. So my fractional error is 0.011. Error over actual value. Then my percentage error is fractional error times 100 over 1, which is now 0.011 times 100 over 1. That will give me 1.116. So percent. That is my percentage error, 1.116%. So I think I've driven this point home. This calculation is clear. So when you are adding, whether the thing repeats, remember it's this repeated here, but when I want to get my mean, I add all of them. This plus 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 this will give me 62.7. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 in number of reading. So I got this. Then standard error in the mean is going to be the highest number minus the lowest number here. The highest number is this, and this should be the lowest number. And divided by the number of reading, we all know is 10. Then fractional error is error over actual value. We give you fractional error. Then if you multiply fractional error times 100, you give you percentage error. I think that is very, very clear for that. Okay, let's look at standard error in slope. Standard error in slope is calculated as, we have seen standard error in mean, remember? We have seen fractional error. We have seen percentage error. We have seen mean. Standard error in mean. Fractional error. Percentage error. We are looking at standard error in slope now. Standard error in slope, SG equals to 4W over NR. So that W becomes vertical scatter, N becomes number of points, and R becomes range. This thing you used to do when you are doing your physics manual. So to calculate your standard error in slope, when you are plotting your slope, you now calculate your standard error in slope. I made emphasis on this when we, earlier in the part 1, when we did something like this. If this is my graph, if this is my graph and this is my best line, I want to remind us something. Remember, the one that is farthest, I take, okay, I pin this side to this side, and I have my W. This W you are writing here now is this W. Is a vertical scatter. Then the slope, which is the Y over the X. So having gotten your slope, for you to get your standard error in slope, you get your W. Now, there's always a lot of controversy on how to get the value of this W. It's very simple. There's no hard and fast rule to it. Take your ruler and measure from here to here. Some person will say you trace here, and you trace here. You trace, I don't know what they are tracing again, but to be quick, exam is all about time. What you are going to do is take your ruler and measure from here to here. It will give you the value in centimeter. And once you get the value in centimeter, use it. You would also be correct, okay? Because what we are talking about is error. It's already an error, okay? So you get the value of W. The value of number of points plotted, 1, 2, 3, 4, 5, 6. Whether you enter or you don't enter, count all of them. Now you go form your N. Then the range is the highest minus the lowest. Now, let me tell you something. You don't pick the range from the graph. You go back to the table. If you are plotting a graph of L against T squared, okay, my range is, since my T square is my x-axis, my range is going to be, I will go to the table and look for the column of T square, The highest number there minus the lowest number there will give me my range. I believe this is well understood. So that is what when you do that. Now listen very well, listen very carefully. In the exam, because it must be in the exam. When you are asked to calculate standard error in slope, which you must be asked to calculate, you state that standard error in slope, SG, is equal to 4W over NR. Please tell us that W is this, tell us that N is this, and tell us that R is this. If you don't mention these things, you will lose mark for that. So that you don't lose your mark, you have to state these things for us. You state this formula, you state this, then you start doing your solving. So if you want to now solve, the value of W, you put it here, the value of N, you put it here, the value of R, you put it here, 4 times whatever is here, then this times this, you do your calculation, and you get your standard error in slope. Another error we can get is what we call standard error in the y-intercept. Standard error in the y-intercept. Now, when you look at when you have an intercept and you're asking to find the standard error in the y-intercept, now it's going to be error in y-intercept. Standard error in y-intercept is w over n squared plus x bar sg. So this was one of the experiments in your manual. So w still becomes vertical scatter. This one you may not need to be writing it out like this. You know that w is vertical scatter. Hope you know, or you can write it out. W is vertical scatter. The n is number of points. X is mean along x-axis. Then SG is standard error in slope. So that when you list this thing for us like this, then you start picking it. So vertical scatter, you pick the value. Number of points plotted, you can do that. Then mean, you go to the X column, just the way that place you went to get your range. You go to that column, add it together, then divide it by total number they are. Let me say you have 1.3, 1.4, 1.6, 1.8, 2.2. That is under t square. So you are going to do this plus this plus this plus this plus this divided by 1, 2, 3, 4, 5. Divided by 5, you will get your x bar. Then standard error in slope. That means you must have calculated this before. The value of SG here now. You come and put it here. And you get standard error in the y-intercept. So standard error in the y-intercept is different from standard error in the slope. Mark their formulas. I want to show us one example from our manual to draw these 2 points. Okay, we want to learn about combination of errors. Combination of errors. Okay. Combination of errors. First of all, combination of maximum error. We want to pick I. Combination of maximum error. Now, I want to just show us some things, some simple calculation that you need to apply. Then I will use an example to draw the point home so that we will not have any issue with that. So, combination of maximum error. There is maximum error, there is standard error. Okay. So let us look at combination of maximum error. Now, for plus, if you have something like arrow is equals to x plus y. Now, see something. This is just like you have an equation like arrow is equals to x plus y. Then I ask you to find error in the r. Error in r. Remember that relationship between this guy and this guy is positive, addition. So I'm going to be having error in r will be equals to error in x plus error in y. That is for maximum error. Do you get that? Now, another one, when arrow is equals to kx, let me put this, x, y, z. If you watch the relationship between these ones is multiplication. So error in r over r will give me error in x over x plus error in y over y plus error in z over z. You see? So that error in r becomes r into error in x over x plus error in y over y plus error in z over z. This becomes error combination, maximum error combination for products. What if you have r is equals to x raised to power l y? Ask us to find error. This one has exponential, so I'm going to be having error in r over r is equals to l error in x over x plus error in y over y. So that error in r becomes r into l error in x over x plus error in y over y. And this becomes the formula you're looking for maximum error. Okay. I think That are all we need for maximum error. There is something I want to say about maximum error. When you are taking an experiment, and when you take a reading, a unit reading, you take the error immediately with it. That type of error is called maximum error. Like, if I'm going to put an example up, we are going to see, so that will help us to drive this point home. Okay, so this is combination for maximum error. For plus and minus, even if you have something like this, okay, let me complete this one like this, so that it will not look as if I just say plus and minus, I did not do anything here. Okay, minus z. Error in R will become error in X plus error in Y plus error in Z. There is no negative error. There is no negative. So this one, though it will look like this, plus minus error in Z, then modulus, of which if you modulize this in, it will turn back to what? Plus. It will return back to plus. So there is no need stressing yourself. You just call it error in Z. That means we don't have negative error, and we don't have error in a constant. You cannot find error in 2. You cannot find error in 3. When you have a constant, you can't get error in a constant. So this is what we mean. So there is no negative error. Okay, let's go to the next one. A combination of standard error. Combination of standard error. Let's go to that one. This one now be standard error. Combination of standard error. Okay. Then when we have, first of all, we have R equals to X plus Y, let's say minus Z. So standard error, S means standard, all squared equals to standard error in X plus standard error in Y plus standard error in Z. So that standard error in R becomes standard error in X plus standard error in Y plus standard error in Z. And that is for standard error. You see how it differs from maximum error. It's kind of different from maximum error. So that we go to another one. If I have that arrow is equals to X, Y, Z, and they ask me to find standard error in R. Standard error in R over R squared equals to standard error in X all squared over X squared plus standard error in Y all squared over Y squared plus standard error in Z all squared over Z squared. You see that? So that standard error in R becomes, so that standard error in R becomes R squared into standard error in X all squared over X squared plus Y squared over plus Z over Z squared, all taking root. You see that? This becomes standard error when it is multiplication. When it is plus or minus, when it is multiplication. Okay, what of standard error when it has exponential? R is equals to X raised power L, Y raised power M. Let's then standard error in R all squared over R squared equals to, you have this will become L squared, standard error in X all squared, do you see that? Over X squared plus M squared, standard error in Y all squared over Y squared. So that standard error in R becomes R squared into L squared, standard error in L all squared over X squared plus M squared, standard error in Y all squared over Y squared, and this becomes our final seat. So this is standard error when it is exponential. Okay. Okay. Someone will say, what's the meaning of all this? I'll give an example to show that. Now, we have seen maximum error, we have seen standard error. Now, relationship between maximum error and standard error. So we should know that E is equals to 3S, where E is maximum error and S equals to standard error. So I believe that. So let's look at some examples to drive all these points home. Now let's take one example from the manual, the physics manual. Now, if you go to page 114, there's something I want to show us there. The question there says, question 1 says, plot a graph of M on the vertical axis and extension X. Okay, calculate the slope S1. So X1 means slope of the first graph. Plot a graph of M against T square, question number 3. Calculate the slope S2 for the second graph, okay? Now, question number 3 says, determine the intercept on the M axis for the second graph. Now, the first graph actually will go like this. That is a graph of M against X. M in gram against X in centimeter. That graph is a straight line graph coming from the origin. That graph is a straight line graph coming from the origin. Okay. Now, the next graph is a graph of M in gram against T square in second square. Now, that graph is going to go like this. So note it, a graph of M against T square for spiral spring. For spiral spring, a graph of M. So here is going to be the slope. So if you watch here, so that is the two graph. So for slope of this one is what they are called x1, and the slope of this one is what they called s2. Okay, let's see something. It say plot a graph of m against t squared. There it say calculate the slope of s2. Say determine the intercept on the m axis. Now you see this thing cut. See where it came to cut the m axis, and it cut it. This is positive y. This is negative y. Hope you know. So it's going to give you a negative answer minus something. So you now say equate the intercept to MO. So you say MO is equals to whatever you have here. Let me say minus 50 grams. That's what that question has us to do. Now you now say if P is equals to, now see something. You say if P is equals to 4 pi squared S2 over S1. You now says compute for the value of P. So you just say P will be equals to 4 pi squared times the value of S1 you got here, sorry, S2 you got here, over the value of S1 you got here, will give you the value of P. Do you get that now? Now move forward to say, what is the physical interpretation of P? It is acceleration due to gravity. Because if you check, it's going to give you, the unit of this is going to be meter per second. So it's going to be acceleration due to gravity. That is that question number 8. Estimate the error in P and MO. Now, error in P. That is where we now come. Now, you see that this is an experiment that has been done. Then we now want to find error. That type of error we are going to find is what we call standard error. But as you are doing it, you are giving the error immediately. That one is called maximum error. So we are going to find standard error in P. Remember that this is the equation of P. So it's from here we are going to find. That is like, that's nice to say r equals to x plus y. See, I'm now p equals to this over this. Now, for me to find error in p, do you know that this one, they are constant and we cannot find error in constant. So p automatically become s2 over s1. Did you see that? Now, do you know that we did not see something like this when we are doing error? So, but do you know this is something as p is equals to s2 times s1 raised power minus 1. You know that. You know that this and this are the same. And it is also like this, s2 times minus 1 s1, that it will drop. So, and you know that there is no, so error in p now over, since it is standard error now, it's going to be error in p all squared over p squared equals to error in s2 all squared over s2 all squared plus minus 1 error in s1 all squared minus 1 all squared over s1 all squared. Do you remember what I'm doing? So that error in p all squared, okay, let me, becomes p squared error in s2 all squared over s2 all squared plus minus 1 squared will give me minus, will give me 1. 1 times this will give me plus error in s1 all squared over s1 all squared. Then all into raised power half, or I put it this way for benefit of doubt. Did you see that? So that way, that is how to get the value for estimate the error in p. This is a formula we are going to use, a standard error. If you go back to what we have learned, you will see that when we say that r is equals to xy, for standard error, we say standard error in r all squared over r squared equals to standard error in x all squared over x squared plus standard error in y all squared over y squared. That's what we go. So if now p is equals to this times this, then standard error in p all squared over p squared equals to standard error in s2 all squared over s2 squared. This is what I'm doing. Plus, now this one is having exponential. Remember, there is one that has the power will drop. You also square the power. You also square the power. If you square this power now, it will give you positive 1. So it's going to be positive 1 times this, give you this over this. So you see that that is where the application is actually is. So this is error in P. Now, the next one says we should find standard error in M naught. Remember that M naught was gotten from the y-intercept. We have something like this, and this is M naught. So it's an error that will be in the y-intercept. So standard error in M will be equal to standard error in the y-intercept, which is something as root of what? W over n all squared plus x bar sg all squared. I believe we still remember this. That will be standard error in the y-intercept. Remember what these values are. So that means for me to get this error in S2, I have to go and look for standard error in the slope. Go back to the experiment, calculate your standard error in slope in the slope 1, calculate your standard error in the slope 2. This is the value of the slope itself. This is the value of the slope itself. This is value of standard error in the slope for this S1, standard error in the slope for this S2. P, we have the value of P. When you say 4 pi squared times S2 over S1 gives you the value of P. So all this we put inside here and you get the error in P and also error in the M-intercept using the standard error in the Y-intercept. So you've seen how to use standard error in Y-intercept when what they are asking you is an intercept on the Y-axis and they ask you to find error about it. you use this for your error analysis. I believe this is very okay. We'll try maybe one more example so that we can now say goodbye to error analysis.